Hi everyone, this is exercise 5 from lecture 4, and we've got a box of toys that a child's pushing along, and we want to find out various things about it, such as the vertical component of the applied force, the horizontal, so on and so forth. If we go through and solve all of the forces that we'll see, we'll end up having solved all of these. The final one we're trying to find is the coefficient of friction. So we're going to draw our free body diagram. I'll try to fit it a bit more on one page this time. So if I draw my diagram here, oh, there we go. And just if you didn't catch this, this is the free body diagram that we're drawing. Free body diagram. Okay, and that shows all of the forces on this box of toys. And we know this box of toys is 25 kilograms. Now, they're pushing it along the carpeted floor with a force of 100 newtons. There'll be an applied force. So we're going to call it FA, and it's at an angle of 30 degrees from the horizontal. As I said, it's going to come in this way and intersect with the center of the mass. 30 degrees from the horizontal, so we can either draw a horizontal here, say that's 30 in there, or if we drew the horizontal in here, it would also be 30 from there. The mark in here, the angle in there, is a more useful one because it's from the start of the vector to the end of the vector, and that's the one that we would use when working out what the x and y components of that vector is. But it is the same size as that 30 degrees from the horizontal. Let's do that. Other forces that exist here will be the weight force, my usual favourite one. Okay, Fw for the force due to its weight, which is mass times acceleration, which is 25 kilograms multiplied by 9.81 meters per second squared, which equals 25 times 9.81 is 245.25. 245.25 kilogram meters per second squared. And if we remember or we forget, okay, F equals ma, and if this is in our standard units of kilograms and meters per second squared, that is the same as 1 Newton. So where I see this, I could instead write 245.25 newtons. They are the same unit. Let's just make this a bit neater. There we go. Now, it says here that the box moves with a constant speed. If it's a constant speed, that's mentioned in Newton's first law. And Newton's first law says that if there are no unbalanced forces, then an object will either continue moving at a constant speed or continue to be at rest. There's no change in its speed or velocity. As it says it's going at a constant speed, we're going to say that all the forces are balanced. Okay? So since it has a constant speed, might write this up here. Since there is a constant speed, the speed is constant, then the forces are balanced. Right? If the forces are balanced, that's saying the sum of the forces in the x direction is equal to 0, and the sum of the forces in the y direction is equal to 0. What's stopping this from falling through the floor then? Okay, the sum has to be 0. We of course have the normal force, which, yeah. which I'll draw a bit longer because I know it'll be a bit longer. If you're not sure, just draw a vector and say this will be Fn, and we'll have to work out how big Fn will be by going through these long equations. We've also got a force that is being applied partially. Part of it will be down. Draw this across. This of course has, didn't label that one, Fa. Okay, we've got the Fa in the y direction, and we've of course got Fa in the x direction. So if this and this should be counted by our normal force, and our Fa in the x direction needs to be counted by another force. Now, I have suggested that we might, in a different colour, just show that the velocity is going in that direction, towards the right-hand side of the page. And if the velocity is in the right-hand direction, our friction force, okay, is going to be in the opposite direction to our velocity. So that's pointing to the left of the page. The friction force is always going to be trying to slow down the object. It's always trying to bring it to a rest. Okay, so our friction force is what's going to oppose our applied force, and our normal force is what is going to oppose our weight force and part of the downward force of the applied force. So let's make our table. We know this is how we're going to solve this question at the end, but we've still got to fill out our table, and I'll put it over this side to see if I can fit it all on one table this time. Okie dokie. We start with one of the forces. Let's start with Fa. Start with Fa. I didn't write its size on there. Fa was 100 newtons. Okay, Fa will be 100 newtons. So here, my usual Fa cos theta, and I'm going to measure, as always, theta will be from my, guess what I didn't draw on there? My x, my y axis. Y, x. Okay, if I don't have those labeled on there, I can't find my angle from my x-axis towards y and continue around in that direction, or from the x-axis anti-clockwise, if you've got x and y in the usual positions. Otherwise, you want to measure it x towards y, whichever way that happens to be. The angle there that we're going to use for Fa can either be past 90, past 180, past 270, and the leftover 60 in there. So 270 degrees plus 60, which will equal 330 degrees. Or you can use minus 30 degrees in there. And in most of the problems I use a positive number. Here I'll use minus 30. So I'll have 100 newtons. I'll put the unit at the end. 100 cos minus 30. Okay, and that will still work out the same as if we use 330 in there. And calculator says 100 cos bracket minus 30 is 86.6 newtons. So Fa in the x direction is 86.6 newtons. Now do Fa in the y direction. Fa sine theta. Again, theta will be the same numbers I've used over here. Okay, so my Fa will be the same size, my angle will be the same size. The only difference is I use cos and sine in different spots. So again, 100 sine minus 30 degrees. So 100 sine minus 30 degrees, you know, minus 50. So the applied force, Fa, in the y direction equals 50 newtons. Just put those in brackets so we know that they're units. Right here, that's Fa taken care of. Our next force we might look at, we'll do the friction force last because I don't think we know what it is yet. We'll do our weight force. Fw is 245.25 newtons. Let's fit that in there. Okay. FW cos theta and FW sine theta. Same size, 245.25 cos, and my angle here, if I draw a little set, let's pick that color, draw a little set of axes over here. Okay, I can either go positive 90 is nice right angle, 90, 180, 270, or I can go minus 90 degrees in the wrong direction, which I'll do this time. So 245.25, oops, cos of minus 90. Let's jump back there. Minus 90, we have 245.25 cos of minus 90. Put the minus 90 in brackets in case your calculator objects, and we get 0. The weight force in the x direction has 0. And that makes sense because it's entirely in the y direction. So we should find that we've got 245.25 sine of minus 90, and sine of minus 90 should be minus 1. Sine of minus 90 is minus 1, so we've pretty much got minus 1 times this number. The weight force in the y direction is equal to minus 245.25 newtons. I should put that in there. Okay, it's minus because it's in the negative y direction. And we go down. Yeah, let's see how much in one page we can fit this. We have the, what have we got? We've got the normal force. So Fn is going to be Fn cos theta and Fn sine theta. Okay, same pattern as per always, except now I don't know how big Fn is. Cos of, what's my angle here? Fn. So if I draw a little set of axes at the bottom of Fn, I can see that this is positive 90 degrees. So I've got 90 degrees here. And cos of 90 should give me 0. Yeah. So this will end up being Fn in the x direction is 0, because it's entirely in the y direction. Fn sine of 90. Sine of 90 will be 1, so Fn in the y direction is equal to just Fn. The absolute size of Fn is all in the y direction. And then our final thing that we have to write in our diagram is our friction force. Ff, which we don't know the size of. We can observe the size of it should be the same as Fa in the x direction, but we'll just double check that with all our maths. We've got Ff cos theta, Ff sine theta. Slipped in a lowercase there. Leave that as a capital. Usually if I'm doing this on pen and paper, I'll do lowercase for my subscripts there. I just happen to write uppercase when I'm writing it on a computer. Sine theta. The angle of the friction force. Draw my little axes here with, x and y. As long as you've got x and y on one set of your axes, like here and here, you should be alright, because that should be representative of everywhere where it is on the diagram. Usually that should be centered on your mass in the center. I forgot about it until a bit later, so it ended up off to the side. Over here, from the x-axis, positive going around, that's 90, that's 180. So I have my angle here, it's going to be 180 degrees. My friction force, cos of 180, and my friction force, sine of 180. Okay, cos of 180. So I can't work out what the absolute answer is, but I can simplify this part down to a number, which simplifies down to -1. So my friction force in the x direction is equal to minus the size of my friction force. And my friction force in the y direction is equal to sine of 180, should be 0, so it's just equal to 0. Now I can do the sums if I find a spot. There we go. So this spot is the sum of the forces. And up the top, which I've just scrolled past, I said the sum of x would equal 0, sum of the forces in the x direction, sorry, and the sum of the forces in the y direction. We don't draw on velocity here because it won't have an impact with any of these and it'll just confuse the process. Remember we said sum of the forces, so it should only be the forces that we're going to sum up. Sum of the forces, so down here we have 86.6 newtons. 86.6 plus 0 plus 0 plus minus the friction force equals 0. Well, we're just going to steal a bit over here. And we can see here that if we add the friction force to both sides, we've got 86.6 is equal to the friction force, and therefore I've got a solution for the size of the friction force. Do I need that over here? I might. No, I don't actually, which is great. So here, the sum of the forces is 50 newtons plus minus 245.25. So minus 245.25 plus, I'm going to run out of room, Fn plus 0 equals 0. Okay, well, I'll steal a bit more. Just nudge this over to this side. Whoop. Equals 0. So here I'm going to work out what this number is first. Let's just duck down a bit. There we go. So 50 plus a negative number plus minus 245.25 is equal to minus 195. 95.25 plus our Fn, our normal force, is equal to 0. So now I'm going to add 195.25 to each side, and I get Fn is equal to 195.25. The only thing left to calculate is if we go back to our question, because we can see we have done the vertical component of the applied force. It's in our table, this one. If you were doing this for an exam question, you would say the vertical component of the applied force and distinctly point out which one of these numbers is the thing that you found. The horizontal component of the applied force over here. We haven't actually said that x is horizontal, so you would want to point that out. The normal reaction force, I found it down the bottom there. The force of the friction, we've calculated that down here, and the coefficient of friction is the last thing left to do. On your page of notes, you will find the equation for friction, which says F, the friction force, in lowercase, is equal to mu times Fn. Okay. This mu is the coefficient of friction. Since this box is moving, it will be the kinetic coefficient of friction. And we know Ff, we've found it over here. And we know Fn, we've found it over here. So we just rearrange this equation to get the coefficient of kinetic friction by itself. So I'm going to divide both sides by Fn. We get Ff over Fn is equal to mu Okay, fill in our values, which is 86.6 over 195.25, and that is equal to mu k, and this as a number is 86.6 divided by 195.25 is equal to 0.44, about 0.44. And I will that looks about right. Why did that work out differently in class? Oh, something's gone wrong here. What's gone wrong here is this applied force. 100 sine minus 30. 100 sine minus 30 was minus 50. Okay. That should be minus 50, which I should have observed here because it's in the negative y direction. Okay, that minus 50 will be minus 50 here, which will instead make this 295. Might just put all these corrections in a different color. Okay, this should be minus 50 because this is a negative in the negative y direction. And if that's there, this will be minus 50, which will make this minus 295. 295, and now I've got 86.6 divided by 295.25, which gives us 0.23. No, sorry, 0.29. 0.29, which is approximately equal to 0.3. So mu k, the coefficient of kinetic friction in this example of that carpet, is approximately 0.3. Okay. As I say, be careful of this. I think it was when I was reading it off my calculator, I just ignored the negative sign, and then I didn't go back and check it. The only reason I did is because I thought that number was wrong. But logically, those two numbers, the downward force and the weight force, are only counteracted by Fn, so they should add together to, the magnitude of it should be added together to get our Fn, and Fn should be in the other direction, so it's a positive value where these two are negative values. And there we go, that's how we solve that one and identify where we've made a mistake. Okay, see you later.